Greetings everyone, and welcome to an introduction to our first modeling method, our new modeling method in the energy unit, energy pie charts. Pie charts are a wonderful way to describe energy because they have a size, so an amount of energy if you will, and you can split up a pie of course into pieces, pieces which represent the different storage mechanisms, the different ways that we can store our ability to produce change. So basically I'm going to go through three labs, a couple that we've done and one that we haven't yet, and talk about them from an energy perspective. So first of all, remember the first physics lab we did, the toy car lab. You might remember in the toy car lab, the whole point of it was to discover constant velocity motion. So let's consider that toy car as it moves at constant velocity across the table. Now here are three distinct positions, and it's moving at all three positions. See the little arrow above it, and the arrow's the same size, so that means it's moving constantly. If we're going to examine this from an energy perspective, instead of writing the equations of the motions or the graphs or the motion maps that we've done in the past, we first need to define a system. Now a system is composed of objects, of things. So the first obvious thing we might want to put in the system is the toy car itself. Second one might not be as obvious, that's the table. And then the third one, the Earth. We're always going to want to put the Earth in the system, as you'll see why here in a moment. So if those are our three objects, let's show that by sketching a little system boundary, if you will, a little dotted line. Notice that the system boundary encompasses the toy car, the table, and even reaches down here into the Earth, if you will. And I don't really care which one you circle in. You could circle in one or three. In fact, you could dot in the entire thing if you wanted to, just so long as you get the toy car, the table, and the Earth. So now that we've defined our system, our question here that we need to answer first is the system isolated? Well, remember that in mechanics that means, are there external forces? Forces coming from things outside the system. Well, let's think about the forces acting on the toy car. There'd be the force of gravity, which is exerted by the Earth on the toy car. Those are both in the system. This is why you always put the Earth into system. That way the force of gravity is an internal force. There's a normal force, a support force, but that's between the table and the toy car, both in the system. There might be friction. That's between the table and the toy car. And then there are forces going on inside of the toy car, but that's inside of the system as well. So as long as we're neglecting, say, air resistance effects here, or we're wrapping them into the friction, then all of our forces are internal, and therefore our system is isolated. There are no external forces. What would an external force look like in this case? Well, maybe if you reached down and shoved the car, gave it a little push, right? Which we didn't do with the toy car. We just let it go on its own. Now, the big idea we learned yesterday is that if it is an isolated system, then the energy is conserved. And that means the total amount of energy at position 1 is the same as at position 2 is the same as at position 3. And if we're going to draw pies, one pie for each position, if they're going to have the same amount of energy, they should be the same size. So here's pi 1, pi 2, pi 3. Again, notice how visual this is here, right? They're all the same size, so the total amount of energy hasn't changed. Now we just have to decide with what our pies are filled. Now, what are our energy storage mechanisms? Well, let's run through them here. First of all, is there any kinetic energy at position 1? Now, kinetic energy is the energy of motion. So, since the car is moving, remember it was moving at constant velocity, it was already moving when we started the timer, there is kinetic energy in this first pie. Since it's moving at a constant velocity, how much kinetic energy must there be in the second pie compared to the first? And the third pie compared to the first? Well, if this is the energy of motion and it's moving the same, it would stand to reason that there would be the same amount of kinetic energy in pi 2 and pi 3 as in pi 1. But then we've run into a bit of a problem. Because when we get to pi 2, not only should there be some kinetic energy, but there won't be any gravitational potential. It's still on the ground. There won't be any elastic potential. There were no springs involved. However, the car definitely did dissipate energy. There were moving parts rubbing against one another. There was sound coming out of it, quite a bit of sound for some of them. And so there was definitely energy dissipated. So how can we possibly add in some dissipated energy and have the same amount of kinetic and keep the pie the same size? Well, we can't. So we have to actually go back to pi 1. We forgot something. there is another energy storage mechanism inside of the toy car. Think about it. What do the toy cars run on? Ah, that's right. There's a battery in the toy car. Isn't that what a battery is? I mean, a battery is literally an energy storage mechanism. And so since that's inside of our system, we need to include it in our pie charts. So I'm going to make half the pie chart battery energy, EBAT. You could call it chemical potential energy if you want to be specific. EChem, maybe. And half EK. Now, do we know that these are exactly half and half? No. Okay, I'm just got to pick something at this point till we get equations and can calculate numbers. Okay, so we're just going to do these kind of relative to one another. So there's got to be some battery and some kinetic. Now, in pi 2, there'll be the same amount of kinetic. Pi 3, there'll be the same amount of kinetic because it's moving at the same speed. However, in pi 2, there will be a bit of dissipated. So notice the rest of the pi is battery. Notice here that the battery is getting less. And then there'll be more dissipated energy. By the way, once you dissipate energy, you just dissipate more energy. And then less battery. So in other words, as we run the car, we run the battery down more and more and more. Now you might be saying to yourself, wait a minute, how come there's no dissipated energy in the first pi? After all, it was running before that. And that's true, but pi number 1 is always 0 time. That's when we started the watch. That's when we started to examine what happened with the toy car. So basically, there'll never be dissipated energy in your first pi. Nothing's happened yet to dissipate the energy. That's 0 time if you're with me. Okay, so there won't ever be dissipated energy in the first pi. Now, if we let the car run and run and run, what would happen? Well, the dissipated energy would continue to grow. The battery energy would continue to decrease. Eventually, we'd run out the battery. Then the dissipated energy would start to eat into the kinetic energy. And if the kinetic energy was smaller, what would happen to the car? It would slow down. And if we kept it running, running, and running, and running, what would happen eventually? Eventually, we would end up with all dissipated energy. The eventual heat death of all mechanical systems, closed, isolated mechanical systems. This is actually one of the laws of thermodynamics. In any closed, isolated system, you must have what's called increasing entropy, increasing disorder. And that means you have to have more and more dissipated energy as a real mechanical system runs. Now, we could idealize this. I mean, for one run of our toy car, was there really that much energy dissipated? No. All right, but unless we're idealizing, eventually your last pi is always all E-dis. It's one of the laws of thermodynamics, one of the invaluable and inalienable laws of physics. In fact, if anybody tries to tell you that they have a perpetual motion machine, can't happen. Any mechanical system is going to dissipate energy, any real mechanical system, and therefore it can't run forever unless you're adding energy in to keep it running.
I'm worried about the kids, homie. Lisa's becoming very obsessive. This morning, I caught her trying to dissect her own raincoat.
I know. And this perpetual motion machine she made today is a joke. It just keeps going faster and faster.
And Bart isn't doing very well either. He needs boundaries and structure. There's something about flying a kite at night that's so unwholesome.
Hello, Mother dear.
Oh, that's it. We have to get them back to school.
I'm with you, Marge. Lisa, get in here. In this house, we obey the laws of thermodynamics.
Ah, Homer. Even he understands you can't have a perpetual motion machine. Always increasing dissipated energy, unless we're idealizing. Our second lab was the disk spinning down an incline lab. Why is it hitting a bowling ball? I don't know, because it can. This was a lab where we investigated uniformly accelerated motion. So let's consider that disk spinning down the incline. It started from rest at the top, and then it got faster and faster and faster. Notice that like a motion map here, these dots are getting further and further apart, and notice here the little dot's not moving, then it's moving faster and faster. Right? So I want to look at these 4 different positions of this motion of this disk from an energy perspective. So first step, let's define our system. Let's put in the disk, the incline, and the earth. Right? And then we have to decide if there's going to be friction. I'm going to say no, just for kicks. Now, technically, there had to be some friction, but I don't really think it was sliding down. It was pretty much perfectly rolling. So I'm going to say no here. If you added in friction, what would be different? You would have to have dissipated energy. So I'm idealizing. I'm saying no friction, therefore no dissipated. So there's our system. Right? Notice the disk, the incline, and the earth. So we're reaching all the way down to the earth there, okay, both visually and by writing it out. So our next question, is the system isolated? Are there any external forces? Well, what forces act on the disk? Gravity, but that's between the disk and the earth. Right? Normal force, that's between the disk and the incline. Even if there was friction, it would be between the disk and the incline. And that's it. Right? So is it isolated? Yeah, it's isolated. Which means, again, energy is conserved. So if we were to draw pies of energy at position 1 compared to 2 compared to 3 compared to 4, they would all be the same size. Now, what are these pies going to be filled with? Well, at position 1, is there any kinetic energy? No, because it's not moving. Right? Not moving yet, no kinetic. Any gravitational potential energy? Yeah, because it's high up in the air, it can move down, right? It'll fall. So there's gravitational potential. Elastic potential? No, no springs. There's no elastic in any of these. Any dissipated? No, for 2 reasons. First of all, nothing's happened yet. And secondly, we said no to friction. So that means the first pi is all gravitational potential energy. Pi 2, we're about a quarter of the way down. So what's going to happen to the gravitational potential energy? The ability to produce change because of its location in a gravitational field. Well, hopefully you see that there'll be a little less gravitational potential. I'm going to say about a quarter less because it's about a quarter of the way down. Now, I don't have an equation yet, but that seems to make sense. So what will the rest of this be filled with? Well, no E-dis, no EE, but it is moving, so there'll be kinetic energy. Pi 3, we're now about half the way down. So that means there'll only be about half as much EG as there was initially. The rest will be EK. And all the way at the bottom, well, now it can't fall any further. So there's no more EG, so it'll all be EK. Notice, this is showing you accelerated motion because the kinetic energy is getting greater and greater and greater. It's also showing you that it's getting lower and lower and lower. And since there's no dissipated energy, it would just keep moving forever. The whole idea of inertia, but from an energy standpoint. Once something has kinetic energy, it'll keep that kinetic energy unless something changes. Our third example is a pendulum. Now, we didn't do this experiment yet. We will in a few units, but I just wanted to kind of look at a pendulum. It makes a nice energy approach. So there's the pendulum swinging back and forth. Now, I'm not going to analyze that much of it. I only want to analyze a half a swing. Okay, from one end to the other. Watch that again. So it's at rest here, and it's at rest at 5. All right, 1 and 5 are the endpoints, and it's swinging through. 3 is all the way at the bottom. Right? 2 is about halfway down. 4 is about halfway up. Right? So it's swinging there. System, pendulum bob. That's technically what you call this thing at the end. The string, the clamp that it's tied up to up here, and the earth. Let's put everything in the system. Why? Because then are there any external forces? No, there aren't, right? Now, before we go there and start doing energy, how can we tell if there's dissipated energy in this one? I didn't say whether or not it was a perfect pendulum with no friction. And I didn't even give you a choice like I did in the last one. Examine the diagram and I hope you can see. Do you see? Look at position 1 and look at position 5. Do you see how 5 is lower than 1? Yes. Position 5 is lower than 1, so indeed there will be some dissipated energy here. If there wasn't dissipated energy, it would have to end up just as high as it started so that it could equalize the EG finally as it had initially. Okay. So, is it isolated? Yes. The only forces are between the tension in the string, which is between the string and the bob, gravity, which is between the bob and the earth, force here between the string and the clamp, but they're both in the system. So as long as we're neglecting air resistance effects here, which we generally will because it's too hard to calculate, we'll end up with all internal forces. That's why we put all of these things in the system. And since we did that, that means the total amount of energy is conserved. So we should have 5 equal size pies. Now our question is, what do we fill those pies with? Well, initially, it's not moving, so no kinetic. It is high, so there will be EG. There is no elastic potential in this lab at all because nothing is stretching or compressing. And again, nothing's happened yet, so there can't be any dissipated in pi 1, never in pi 1. Right? So the first pi is all EG. Now, pi 2, we're about half the way down. So we have dissipated a little energy now. Remember, we decided there would be some E dis because 5 is lower than 1. Now, I don't exactly know how much. It would probably be a lot less than this, but it was hard to draw a small piece of pie. So it really would be a thin little sliver because most pendulums don't dissipate a ton of energy. They can swing for quite a while before they stop. Okay, but just relative here. Okay, so there'd be some E dis. Since we're about halfway down, I would guess that about half of the rest is gravitational now. It's lower, right? And the rest, it's now moving, so there's kinetic energy. Notice how we can kind of run through our list of storage mechanisms and decide whether there is any of each. Now, pi 3. There'll be a little more E dis. Okay, and again, I'm exaggerating the amount of dissipated energy. Now, the question is, how much EG is left? Well, no matter what you answered, you're actually right. It's all relative. See, EG depends on its location in a gravitational field, and location depends on what you decide to call 0. There's two kind of places here we might look at. We might say, well, let's call the Earth 0. I mean, that's what we normally do, like in a projectile problem. And if the Earth is 0, then it's above the Earth. And if it's above the Earth, it would have some gravitational potential. However, as long as the pendulum doesn't break, is it ever going to get any lower? No. So why don't we just call this height 0? If we do that, it makes the math easier, right? Because zeros just drop out of equations. So since it's never going to go any lower, let's just call that 0. And by the way, that means that it doesn't matter where this pendulum is tied up. You know, is this pendulum tied up to a clamp that's on top of the table, or is it on top of the or above the floor? Who cares, right? Really, what we need to know is just kind of how long the pendulum is, not exactly where it's tied up, right? So this makes things a lot easier. So realize here that you can make a choice with gravitational potential energy. You can make a convenient choice of 0. So if there's no EG, then what's the rest? Well, it's EK. Why more? Because it's going faster. Right? Now it swings back up. Right? More E dis again. Whatever's dissipating the energy keeps dissipating energy. Notice E dis never gets smaller. Because once you dissipate energy, it stays that way. It's no longer useful to the mechanical system. Now, since we're about halfway up again, I'm going to split it half and half. But notice here, this EG is less than the EG in 2. And you notice how 4 is lower than 2? This EK is smaller than the EK in 2, which means it'd be going slower in 4 than it would in 2. All the way up at the far edge at 5, even more E dis. No more EK, because this is where it's turning around to come back. So it's all EG. But compare. This EG, less than this EG, so not as high. Imagine here what this would look like if we said this was an ideal pendulum. Or if because we were only doing like half a swing, we could just neglect the air resistance and frictional aspects of it. Right? Then we'd be half and half here. We'd be half and half here. And these would be the same heights. We'd be all EG, and we'd be all EK. Right? The fastest it'll move. So I hope you enjoyed this little discussion of the law of conservation of energy using energy pie charts.